So a capacitor. The way we draw a capacitor, that's the picture for a capacitor in circuits. Sometimes we use just straight lines, but normally when you see a curve, this is the plus and that's the minus. That's what that means. And you have a current going through it, we'll call it I. Normally a capacitor is built like a piece of metal like this. There's another one right on top of it. Trying to do a 3-dimension here. But two plates with one wire sticking from this end and one wire from that end. And there's a substance between them. Could be air, could be water, could be glass, could be anything. That will determine the value of the capacitor. Now, the current through a capacitor is equal to C, the value of the capacitor. C is measured in Faraday or farad. C and times the derivative of the voltage, the change in the voltage, dV dt. Also, the current can be is the change in the number of charges per time, dq dt. So if you can count how many charges, if you have like a hole there and you cover with the glass and you can count how many charges went through that in 1 second, that's actually what the current is. I equals dq dt. And I equals C dV dt. Now, let's look at some examples here. If I take a voltage source of 5 volts, now I want you to use your calculus here, and run it across a capacitor. This is the capacitor, and I'll use a number, let's say 1 millifarad. That's 10 to the minus 3. How much current is going to be going through that capacitor? The math said I equals what? C dV dt. What's C equal to? 1 milli. And what's the derivative of the voltage? What is the derivative 5? 0. So what's the current? 0 amps. Why is the derivative 0? In calculus, we know the derivative of any constant is 0. So when you have a DC source, that means your value here is a constant value. Then the derivative of that, derivative of any constant is 0, which implies what? The current through the capacitor will be what? 0. So to a DC source, if the current is 0, that means that capacitor behaves as what? As an open circuit. If there is no current going through it, that means it's going to react like you have an open circuit there. So you'll see us actually down the road when we start doing circuits. If we have a DC source, we take the capacitor and make it an open circuit. Because of that equation, I equals C dVc dt. The voltage across the capacitor with respect to time. Then parallel, they have the same voltage. So if you have a DC source, the derivative is 0, the current is 0, the capacitor is going to react as an open circuit.
So like for a DC source, would there be a limit on that? Like say it was like 100 volts.
Doesn't matter. Derivative is 0. 1,000 volt, derivative is 0. 0.1 volt, derivative is 0. Yep.
In an ideal capacitor, in a real capacitor, you can break it and
Oh yeah.
short.
Yeah, if you take and crank a high voltage into our capacitors, you'll smell them, you'll feel the heat and everything. Sure. You can destroy them, but mathematically,
But ideally,
No.
So never like discharge or
well, what's going to happen actually when you connect that source, it's going to take few seconds, microseconds to charge it. Then after that, it's going to look like a DC source, and that's actually what our study is going to be. What happens from the time you connect that to the time it's completely charged? Because if you look at the voltage right here, across this, if I'm trying to watch it and see what's going on, well, initially that voltage is what? 0. Before you put the source in. There's my voltage is 0. Then what's going to happen? You put that 5 volts, we're saying there's no current going through that. That's an open circuit. Well, if that's an open circuit, what's the voltage here? 5 volts. So what's going to happen to the capacitor is going to charge like this, then it's going to level up 5 volts. Usually that's so quick there, that time here, in the millions or microseconds. Yeah, in a few classes, we're going to focus our study on that time only, what's going on at that time, you know. But for now, that time is so quick, you blink your eye, it's gone, you go to measure the voltage, it's already 5 volts, and that's going to be hit like an open circuit. Lydia. What happens if you have an AC source here? Same problem, but instead of 5 now, and you put again 1 millifarad here, and you put 5 sine 377t. What's the voltage here? Or, well, let's find the current first. What is I equal to? C dV dt. C is the capacitor, which is 1 millifarad. The derivative of the voltage is going to be 5 times what? What's the derivative of sine 377t? 377 cosine 377t. So 5 times 377 times 1, 10 to the minus 3. Get a calculator here.
At 5 times? Okay.
Yep. 1.885 cosine 377t. That's what the current is. So that current is not a constant value. If you watch that current through the capacitor, it's going to look like this. It's a cosine function. And it repeats. The peak value is 1.885. The lowest value is what? Negative 1.885. So to an AC source, that's an AC source, alternating source. Now the current is not 0. It's the derivative. So the only time the current is actually 0 when you have a DC source.
So like, how do you get a capacitor to like discharge?
Unplug the source. You'll hear discharge. Actually, if you have speakers, old speakers attached to your old computer, I have in my office. If I go shut them off, I'm playing like YouTube music, I shut them off. Even after I turn it off completely, it goes down a little bit. You hear that discharge, you know? But if you disconnect the source, this becomes your source, because right now, this has the same voltage, they're in parallel. What happens? You take that source out. Hopefully there's a way for it to discharge, because if it's open, where's the current going to go? So let's say there's another part of the circuit here, then that value will discharge quickly, and we'll talk about the time constant, how quick it's going to charge and discharge. So what is, if I'm looking for the voltage across the capacitor, not for this example, because this example, they're in parallel. But if I can find the current through it, can I, after that, find what the voltage is? Well, let's do the math. I have I equals C dV dt. Okay. If I cross multiply, I dt equals what? C dV. Divide both sides by C. 1 over C I dt equals what? dV. And if I'm looking to solve for V, I'm going to integrate both sides because the integral of the dV is what? V. So this will be 1 over C. The integral, usually go from minus infinity to t, mathematically. And if you want to break it down, you can go 1 over C, the integral from negative infinity to t0, anytime you want it to be, I dt, plus 1 over C, the integral from t0 to t, I dt. Normally for t0.
T0.
Normally T0 for us is the time you go to the lab and you connect the circuit. So that could be 0. Well, this value here that you're looking at, it's the voltage at T0 plus 1 over C, the integral from T0 to T, I dt. And that's the voltage across the capacitor at any given time. Usually that's a constant value, so don't be surprised to see the letter K for that. So you might see the equation, the voltage across the capacitor at any given time, either one is going to say 1 over C from T0 to T, I dt, plus the voltage at T0, or 1 over C, the integral from T0 to T, I dt, plus a constant K. If the initial conditions are 0, then you can drop that piece. Here's an example. Let's see if we can go through it. I'm going to ask a few questions. Given that the current through the capacitor is this picture. This is in milliamp. 0, 20 milliamp, the high value, and this is 2 in millisecond, the time in millisecond. This is the current through the capacitor. I need to find what the voltage is. Find the voltage across the capacitor. Well, I can break it down to 3 parts. I can look at the current and go, you know what that current is? It's 0 for t less than 0. It's 20 milliamp for t greater than or equal to 0, less than 2, I can put the equal sign with either one. It's 0 for t greater than or equal to 2. If we are applying this current, this is the current going through a capacitor, and let me give you the value. It's 5 microfarad. That's the value of the capacitor. So this is the current I going through the capacitor. And the question, what's the voltage across the capacitor? So this current is going through that capacitor. The question, what's the voltage? Let's break it down to the first part, the voltage for t less than 0. It's 1 over c, the integral from minus infinity to 0. And what was the current for t less than 0? 1 over 5 micro. The integral from negative infinity to 0 of 0 dt, and that will be at 0 volts. I'm going to draw the voltage versus the current, top of each other. This is the current, this is the voltage. This is the voltage across the capacitor, this is the current through the capacitor. This is in millisecond. So what we have is 0 up to here. For the current, what do we have here? 0. I'll leave that paper handy. So this is the first part for t less than 0. The voltage for t less than 0 is 0. Okay. What's the voltage from 0 to 2? 2 milliseconds. Let's look at that. So for t greater than 0, less than or equal to 2, the voltage of the capacitor is going to be 1 over c, the integral of 20 milli from 0 to where? To t, any given time, right? dt plus the voltage at 0. If you're starting at 0, you want to add the voltage at 0 to that. I didn't add the voltage at negative infinity. That was 0. Shut off. Remember the equation? The integral, where is it? Right here, at the top. From t0 to t plus the voltage at t0. From 0 to t plus the voltage at 0. These have to match. Well, my voltage at 0 for this example was what? What was the voltage at 0? 0. Is it 5 micro? Bring that one to this side. 20 divided by 5, that's 4 milli. Four T in millivolts. Let me write it, 4T in millivolts. So the voltage is going to be a straight line. 4T So let me graph that. Let's see what it looks like. 4 times t. Going back to my picture. right here, this is what the current was. 20 milliamp. This is 2 millisecond. This is the 2. The current's going to be 4 times t. 4 times t is going to be a straight line. It looks like this. And what's the highest value of that? When t equals 2 here. What's 4 times 2? 8 millivolts. When it's 0, what's 4 times 0? 0. It's going to be a straight line, 0 to 8. Now what's going to happen after that? This has a value of 0. So let's look at the circuit now for t greater than 2 or equal to 2. So it's going to be 1 over c, the integral from where? 2 to t, 0 dt, plus the voltage across the capacitor at 2, whatever that value is.
Maybe the flip, like opposite way.
What is it?
Would it be the flip, like on the negative or going back up?
What's going to flip? This one? Let's see. Let's see if it's going to flip or not. What is the value of the voltage at 2 equals 2 millisecond here? Isn't that 8? 1 over 5 micro. The integral from 2 to t of 0 dt. What's the integral of 0? 0. 0 plus 8 millivolts. Guess what we have? 8 millivolts. So the picture for that, it's going to be straight line forever. 8 millivolts. So the voltage across the inductor is always going to be 1 over c, the integral of I dt, from t0 to t plus the voltage at t0. If this is 2, that's the voltage at 2. If this is 0, that's the voltage at 0. The voltage at 2 happens to be 8 millivolts, and that's why it stays at 8 millivolts.
Now, where are you getting the values for t again?
The picture, right here.
No, but I mean, like in the like when you started, you
Yep.
had like
From that
t
picture.
is less than 0, 0
It
is
came right from the graph.
The graph.
Oh, okay, so it
Right there.
from the graph.
Yep.
Okay. So like I guess what I'm curious is like when we start working on problems for these, like from the book, are they going to show us like a graph?
Yep.
And then we're going to have to
Give you a graph or an equation. Yep.
Okay.
Now, how about the energy stored in a capacitor? Capacitors are called energy storage element. Energy storage element. That's what we call a capacitor. If you listen to the name, energy storage elements. So they store the energy. How much energy is stored in them? Well, let's see. Let's derive the equation for that. What do we know? We know power, it's voltage times current. Which is voltage times, what's the current? I equals C dV dt. So the power is going to be C V dV dt. Now, if you remember the change in energy from physics, it's the integral of power dt. That's equal to It's the integral, energy is the integral of power times dt. Well, let's take that equation, and if you multiply both sides by dt, you have p dt equals cv dv dt. The dt is gone. Multiply both sides of the equation by dt. So the energy is equal to the integral of p dt. Well, what is p dt? It's c v dv. If I take the c outside, what's the integral of v dv? What's the integral of x dx?
X squared.
Yep, v squared over 2. So the energy is going to be 1/2 c v squared. That's how much energy is stored in the system. The amount of energy, you might use W here, in a capacitor, that's the energy, or E, sometimes it's W, it's 1/2 c v squared. So that's the math behind the derivation there. Let me take an example, run it through, and see what we have. Here's my circuit. You'll see when you have an AC source, usually put like plus and a minus with that squiggly line. That tells you an AC source, like sine or cosine. This one, 10 sine, or 100, can't see, 100 sine 2 pi t. (100 sine 2 pi t). We have 1 mega ohm. We have a capacitor of 20 microfarad. And this is the current through the capacitor, I sub C. This is the current through the resistor, I sub R. And this voltage, they all three in parallel, we'll call that V. So this, and this, they all in parallel have the same voltage. The question is, find the maximum energy stored in the capacitor in this picture and the energy dissipated in the resistor over the interval from 0 to 0.5 seconds. We'll calculate that. So let's find the maximum energy stored in the capacitor. Well, the maximum energy stored in the capacitor, it's 1/2 CV squared. 1/2 C is what? 20 micro times the voltage squared.
I guess you want a B max.
We'll come back. What's the voltage? We'll come back here. What's the voltage here? 100 sine 2 pi t. That's the amount of energy stored at any given time. Can we do the math there? That is actually 10 micro, because 10 divided by 2, that's 10 micro. 10 times 10 to the negative 6. 100 squared is what? 10 to the 4th. Sine squared 2 pi t. Is that 0.1, I think? So that's the equation for the amount of energy. If you want to find the maximum value you can have, the maximum value. Well, what is the maximum value a sine can have?
Just one.
1 or minus 1. That's maximum minimum, right? When you square that, that number is going to be what? 1 times 0.1. So the maximum amount of energy that capacitor is going to have in it at any given time is 0.1 joules. So it's between 0 and 0.1 joules. That's what you're going to have stored there. So that's the first part. The next question is, okay, how much energy dissipated to the resistor? Well, let's look at the resistor. Let's calculate the current through the resistor. The current is the voltage divided by 1 mega. The voltage is 100 sine 2 pi t divided by 1 mega, that's 1 million. So what do we have? 2 of these zeros cancel 2. That looks like 10 to the minus 4 sine 2 pi t. Or 2 pi t divided by 10 to the 4th. I can calculate the power to the resistor there. The power, P equals V times I, or I squared times R, or V squared over R. Well, I could use V squared over R. I don't have to calculate the I. That'll be 100 sine 2 pi t times what? 10 to the negative 4 sine 2 pi t. What's that, 10 to the minus 2? Ten to the minus 2 sine squared 2 pi t. And what about the energy? Energy is the integral of power dt. The integral of the power dt. I should put the R down. Which is the integral of 10 to the minus 2 sine 2 pi t. But they wanted this power from where to where? 0 to 0.5 seconds. That's all they're interested in.
So you got the square of the sine.
Yep, sine squared. Now, again, to integrate sine squared, you're in trouble there mathematically. Unless you use the equation, try to break it down. Now, you guys took calc too? U substitute, what is it?
You want to do the U sub?
Let U equals what? Sine squared?
I don't remember.
And U and dV? What is that method called? You let U equals sine squared 2 pi t, you let dV equals dt.
Parts, integration by parts.
Integration by parts. You could. For me, that's an easier approach. I pull out my TI-89 or Mathematica.
So you wouldn't mind if you did that on a test? If you did.
Okay, I'm not teaching calculus. You should know that stuff.
Yeah, I'm gonna order today.
The math people won't like it, but that's their class. So I go to my calculator here. Oh, I got in trouble. I'm in trouble here. I don't have the 89 with me. So I will plug in that on the 89 and I'll be in good shape. So integrate that use TI 89 to integrate. I'm not going to do integration by parts and spend another 5 minutes on it.